Okay. Good morning, everybody. So yesterday, specifically in the afternoon, we looked at the Hopf algebra of multiple polylogarithms. And, well, we mostly looked at examples. So we looked at functional equations. And in the end, we defined a symbol, which, if I may remind you, is nothing but the maximal iteration of the coproduct. And we also discussed the integrability condition, which basically says, well, it's a sufficient and necessary condition for a tensor to be the symbol of a function. Okay, we had the example of, the formula was a bit long, but you have the example of this. You remember the integrability condition tells you have to replace consecutive pairs by d logs, wedges of d logs. And this obviously vanishes, so there is a function whose symbol is this, which in this case is very simple, is log x log y. But if you only had one term, there would be no such function because d log x, which d log y is not 0 in general. Okay. So this tensor is not integrable. And we also looked at amplitudes again. And let me take it from here. First giving you a quick recap and then going into a bit more details. So we looked at the weight. And we said if you have an amplitude that, if I schematically write it in dimreg like this. So what I'm effectively interested in is the coefficients in the Laurent expansion in dimreg. Then, and if I assume that the AKs are multiple polylogs, otherwise we don't know what it is, so we don't know how to make any statement, then the conjecture is, and this conjecture is actually backed up by everything we know, that the weight of the coefficient AK is less or equal to 2L plus K in 4 dimensions. And in n equals planar, n equals for superioring or n equals 4 actually, not only planar, this bound is saturated. And we also looked at, well, discontinuities. And I remind you that discontinuities have the property that the coproduct of a discontinuity is such that it only acts in the first factor. And then if you combine this unitarity, which tells you that in the massless case, so massless means there are no thresholds, it's all just, well, there are no thresholds, so all the branch points, which corresponds to cuts, must be at points where Mandelstam invariants vanish. So branch points correspond to Mandelstam invariants vanishing, or infinity. So this unitarity, this is this, and this, if you combine the two, then you conclude that, for example, the 4-point amplitude, which is a function in the planar limit of only s and t, its symbol must look something like s tensor something plus t tensor something. Because the first entry must have the correct discontinuity, and we know that A4 only has discontinuities when S is equal to 0 or T is equal to 0 in the planar case. Or the other example was our function R6. Well, we called it R6 too, but it could be any number of loops actually. R6 is a function of cross ratios. The branch points must be whenever a Mandelstam invariant vanishes or becomes infinite. And by conformal invariance, that means that the symbol must take this form. So the first entry can only have this form. I remind you that in the symbol, conventionally you drop logs, but this means log S, log T, log U1, log U2, and so on. Just a notation, okay. So I could just as well write it as log S tensor something, log T tensor something, or here log U1 plus log U2 tensor something plus log U3 tensor something. Okay, so the branch cuts are precisely at the locations where you expect them to be. Okay? So this is what we did yesterday. Are there questions about that? No? Okay, then let's elaborate a bit more on this. Because here I just gave you the example of the symbol, which is what's called the first entry condition. You can of course be more general, because this formula holds for all the components of the coproduct, not just the ones that have a log in the first entry. So it means that you can also state it as the first factor in the coproduct of some, let's call it amplitude, but could be Feynman integral, some physical objects that has physical cuts. Can only have cuts corresponding to a Feynman integral or an amplitude. Okay, so schematically, if you want, and we'll see in the rest of the lecture, we'll see examples of this all over the place. If I write schematically the coproduct of an amplitude as, let's call it the left factor tensor the right factor, but there could be many of them, okay, it could be some of such things. This, we know where the cuts are. The cuts come from unitarity. Katkowski's rules, if you want. Which means that L must have the same cuts. So the functional form of L is very much constrained. That's another way to put it. The rest is not. Well, people are thinking about what this thing is. I could be more precise, but this is more on more shaky grounds. Well, this is just, you combine this formula with unitarity and you conclude that this function form of L must be the same as the function form of A. There are actually statements by mathematicians, and I quote it like this because I'm not sure I understand all the mathematical details, that you can prove that if A is a Feynman integral, then L must be a Feynman integral, which is even stronger. You say it's not just a function which has the same cuts, but it must itself be a Feynman integral. There is a general formula for what this thing is if A is a Feynman integral, but I don't understand the formula. It's in terms of some motivic objects that I don't fully digest. But one of the theorems that comes out in the end is that the coproduct of a Feynman integral should be such that the first factor is itself a Feynman integral, which is stronger than just saying this. Okay? Is this more or less clear? if it is clear, then let's look at an example. Let's put all the things together that we've seen so far. Okay, and what is it that we have seen so far? So we looked at planar n equals for super Young Mills. And I will use that as the example as well now. And we looked at kinematics, and we decided that this was given by momentum twister, so by geometry. Let me be more precise for on-shell amplitudes. Because this was all about light rates, all about light like momenta. Okay, keep this in mind. Well, because the first example will not satisfy this, but it's a cleaner example. Then we had this. We said that these things should correspond to leading singularities. And these things, well, are transcendental functions. Could be anything, but let's restrict ourselves to multiple polylogs. And then we can make some claims. We can make some claims about the weight of decay. That's what I just erased what was here. So if M and N equals to super Young Mills and is an L loop object, then the bound should be satisfied. I should get something like 2L. 2L in 4 dimensions. And I also know something about the coproduct of this thing, namely that its first factor here must have the right cuts, which is what we said here. Okay, these are the general statements that we made so far. And one other thing we saw yesterday, we said that the alphabet of when I look at the symbol, what appears in the symbol, I call these entries the alphabet. Those are like logarithms that build up the whole functional space. If I give you this set of logarithms, if I give you the alphabet, you can reconstruct the full functional space by looking at all possible tensors that I can make out of these logarithms, and functions correspond to the integrable tensors in that space. Okay? So these are the very general statements that we have right now. Now let's put this into action. And we're not going to put it into action on amplitudes immediately, but let's first look at 4-point correlators. And actually there was a paper on this stuff just this morning which generalizes what I'm going to say now. So what I'm going to look at is correlators. So I take 4 operators. And let me not be more precise for now. Of this type, okay? I'm looking at an object of this type. Where O are some operators. The operators that I have in mind are operators that correspond to some what is called a stress tensor multiplet. The details are not important for what follows. But if you want to know what it is, T, for example, if it's a supersymmetric multiplet, it would contain the stress tensor as an operator and also the Lagrangian and other stuff. But the details are not important. In particular, the paper this morning generalizes it to large classes of other operators. So let's just say I take some operators, or at least some nice operators, let's put it like that. Details are not important. And so just to give you an idea why people got interested in this, is that, remember, there was this duality, scattering amplitudes which are dual to Wilson loops. Okay. actually the picture extends to triality, where you also have these correlators. And actually super amplitude, super Wilson loops, and there's also super correlators. Where the duality in this direction is whenever 2 points, so these points are in random position, in arbitrary positions, but the statement is whenever all the neighboring points are light-like separated, so whenever, for example, the distance from x1 to x2 is light-like, from x2 to x3 is light-like, x3 to x4 is light-like, x4 to x1 is light-like, then I would get the same as what I have up here. At least at the integrand level. Remember also here we said that the statement should be at the integrand, strictly speaking, at least for the supersymmetric generalization. Okay, this is just to give you the motivation why people started looking at this thing. So the statement was, the conjecture was, at the level of the integrand, I plus 1 square goes to 0, so neighboring points are light-like separated. G, which is my correlator, so this is what I call G4, divided by its, well, or rather, this would be the integral. The integral of G4 would be this. So it's the integrand that I'm looking at. Gn4. This thing would give me the same as the integrand. So you have an MHV amplitude divided by its 3 squared. I put here MHV because I look at bosonic objects. If I want to go beyond MHV, I need to supersymmetrize the picture. But the statement is that the correlator, when the neighboring points become light-like, well, then it gets the same as the amplitude. Of the amplitude. So, I'm in image planar theory. I can give a unique meaning to the integrand because I can go to dual variables, so all my shift symmetries are resolved. So my integration variables take one loop, okay? And actually then you see, already at one loop you see what the correspondence is. At one loop this thing, the correlator, is a position space integral where I have x1 to x4, and I have to integrate over all possible other points I could insert. This gives me a correlator at one loop level. But this is the same as this box in momentum space, which is the thing that sits on the other side. So the integration variables, if you want, are on this side are the dual coordinates, the axis. And if it's planar, then this has a precise meaning because I resolve the shift symmetry over the integrand. If it was not planar, talking about the integrand wouldn't have much sense. Because I could shift the momentum, the loop momentum in different diagrams in different ways, and wouldn't have any sense. Okay? So this is just for the motivation. So the details of this are not important. I just want to tell you why people started looking at this stuff. What I want to do is I will actually compute this thing now perturbatively, order by order, and doing the integrals. So I don't care too much about the relation to the amplitude. So let's compute this thing. Well, at one loop, I already told you what I would get from here. This is planar n equals to 4. Everything I'm going to say is planar, unless I say otherwise, it's planar n equals 4. This, no. First of all, as I said, this, talking about integrands needs planarity. And I have not seen any statements of this type beyond planar n equals 4. Which doesn't mean that you cannot find other theories that have this property, right? Okay, so at one loop, The integral I would need to do for this thing would be something like this. And let me write it. It's the one that I already wrote down. And I neglect prefactors, but the integral that I have to do would look like this. And what the black and white dots are, I'm going to tell you in a second. So this is the integral that we have seen many times by now. This is the integral d for x naught, x1 0 square, x2 0 square, x3 0 square, x4 0 square, and I put a numerator to normalize it in a nice way. This is like the factor st that we had already for the box. Okay, and why do I have black and white ones? Well, it's just simply out of convenience. In my pictures from now on, black ones will be the points that I integrate over, and the white ones will be the external ones. That's just for convenience. Okay, so this would be the integral that you need to compute at one loop. You take this thing, you take the Feynman rules, you work them out. This is the thing that you have to compute. If you think about it, there's not much else it could be. It must be a one loop object, and this is n equals 4, so it's conformal. So it must be a conformal one loop integral. That's pretty much the one it is. But you can work it out rigorously from Feynman rules. Okay? And again, this corresponds to a dual picture, which would be a box integral. This is what we've seen already many times. Okay? So, this, of course, people have done it a long time ago. And before I tell you what the answer is, let's look at two loops, because the answer will be the same pretty much at two loops and at one loop. At two loops, what you get is two things. You have to compute the one loop square integral, which we know. By the way, this integral is finite, because it's completely off shell. And you get the double box. You get an integral which in position space looks like this. And I let you work out what the corresponding integrand is, which is actually just the double box. When you work out what the corresponding dual graph would be, it would be this one. Okay, so that's the double box. Okay, and again, if you remember what, for example, the 4-point amplitude looked like, at one loop it was the single box, which in the correlator language becomes this. The double box was, well, the two loop 4-point amplitude was given by a sum of two double boxes, which is pretty much the same as what you have in the correlator, so that's where you see that something like this will arise at the integrand level. Okay. You can go to three loops, and that's where new things happen. Well, new things in the sense that you don't just get simple box integrals. Three loops. You get everything that is like two loop, one loop times two loop, which we know already. And you have to compute things like this. Which you can easily convince yourself actually corresponds now to the triple box. And if you remember the amplitude, there was another piece, which was the tennis court diagram. And that's also what you get here. The tennis court diagram in position space looks like this. So, indeed, when you go to the dual graph, you get a tennis court diagram. Okay, these are the graphs that we had in the 2-loop 4-point amplitude. There they are on shell, here they are completely off shell. Now, what happens, however, at 3 loops, you get, in the correlator, you get, which is off shell, you get 2 more graphs that will vanish when you go on shell, but they are there off shell. These are graphs that have no direct momentum space equivalent. They look like this. Now drawing gets a bit tricky. So there's a black point in here. And then this one is connected to this point, this is connected to this point. And there are also some dashed lines which are numerator factors. I'm not going to discuss those. And there's another one which looks even worse, which looks like this. This one is connected to here. So if my drawing skill is correct, this should be the graph. Just 1, 2, 3, 4. No, it's not correct. This one is connected to here, to here, to here. This one is also connected like this. And again, some numerator factors that we don't care about. So you see, these things get pretty complicated. And they have no momentum space equivalent because they are non-planar. It looks weird that you get non-planar graphs in n equals 4, but that this is correct. You can show that this must happen. And they vanish when you go on shell. So that's why you don't see them in the amplitude picture. But they are there. Okay, so now you want to compute these things. You can show that by conformal symmetry, all these things are conformal. This one is equal to this one. I'm not going through the argument, but you can show that basically the argument is, you see, there is a 2-loop subgraph in here, which would be, let me write it like this. I can take out this thing, okay, which is precisely this one here. I can rotate it by 90 degrees and plug it back in, and I get this one. And this rotating by 90 degrees you can show is a conformal transformation. Well, you get the same answer because of conformal symmetry if you rotate it by 90 degrees. Why? Because this thing, if it's conformally invariant, they just depend on cross ratios. And you can show that this thing, or the one rotated by 90 degrees, would give you the same cross ratio. It's the same function of cross ratios. Okay, can you see that? When you take the wavy one, you turn it, you plug it back in, you get to this one. So, this one, you know, this one, and this one, they were computed 20 years ago or something like this. Actually, all these ladder type integrals, all the ones that you get by chaining one loop boxes together. They were computed 20 years ago, or something like 20 years ago. Those were called ladder graphs. Those are the graphs that in momentum space look like this. Okay, infinite chains of ladders, and they were given by a function phi at L loops, which depends on two variables u and v that I will define. Those are my cross ratios. Minus 1 to the L plus 1 divided by z minus z bar times the sum from k equals 0 to L minus 1 to the k to L minus k factorial, k factorial, L minus k factorial, L factorial, log to the power k zz bar times Li 2L minus k z minus Li 2L minus k z bar. It's a quite remarkable formula. Okay, this is for any number of loops. You can just write down the answer. It goes back to the Davidovich Venus Yukina. U and V in here. Write it here. You know what we have seen these things. Those are my cross ratios because everything is conformal. 1, 2, 2, 3, 1, 3 square, 2, 4 square, and V is x 1 4 square x 2 3 square divided by 2 3 4 here x 1 3 square x 2 4 square, and z bar are defined by u equals zz bar and 1 minus z bar. And you can check these z and z bar and u and v are pretty much the same as what we had in the first lecture for the 3-point function. Okay? Now, I'm just throwing this at you because this was stuff that was known 20 years ago, so I don't have to care about it. One thing you can notice is that this is an L loop object in n equals 4, and we said that in n equals 4 the bound is saturated, so the weight must be 2L. And you see here that the weight is indeed, so I have Li 2L minus k times log to the k, so the bound is indeed saturated. Okay, but then I also need this integral and this integral. This integral was called. And of course, I need them for all possible assignments of 1, 2, 3, 4 outside, okay? This one was called the easy integral, and this one was called the hard integral, for reasons that probably only the authors of the paper know. Okay, so how would you go about computing these integrals now? And these things are pretty tough, and these are 3-loop integrals with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 propagators. And 6 scales. It's conformal for 2 variables. And this is tough. You can try to do it brute force, say using Feynman parameters, but good luck. So the way you can do it is you do it in 2 steps almost. So the idea is the following. You say, okay, let me guess an ansatz for what this thing should be. Take easy for now, just to fix the idea. You want to kind of make a guess for what this integral could be. Okay, it's like the easy integral. And you say, what could it be? Well, we said it must be something of this type. And let's assume this thing is polylogs. Now, I know that this thing must come from the leading singularities, so I can go and compute them. Now the question is, what kind of ansatz could I use here? This I know in principle how to compute, but how can I get an ansatz for TK? A posteriori. You don't know. You make the ansatz. Yeah. I mean, in all this game, also it will happen here. You will make an ansatz for what this thing could be. You match it to some limit in which you can compute this thing. For example, here the limit will be when 2 points become close, then you develop a singularity, which you can actually predict, because in that limit you know how the singularity develops. You can look at the integon and see how the singularity develops in the integon. You can actually compute it. That was done by people using some kind of OPE techniques and stuff like that. And then you have your ansatz, and you try to match the ansatz in the limit. The limit where 2 points become close corresponds, for example, to u going to 0. And you require that your ansatz has the same expansion in the limit u going to 0 as what you got from OPE, for example, or collinear limits or something like that. Sorry? I mean, if I know the expansion, I need enough terms in the expansion. Then it's enough. Well, I might need more than one limit, okay? I might need different limits, and I need enough terms in the expansion. But if I look at all the limits, then yes, if I have an ansatz which has a finite number of free coefficients, I can fix them and then check that after all the coefficients are fixed, that it is consistent with everything else I know. Or numerically. In this case, it was checked numerically in the end. Okay? So, you want to get an ansatz. So the idea is, make an ansatz. And I haven't told you yet how I get to my ansatz. Make an ansatz. And match the ansatz to some limit. Where you know how to compute, which could be so OPE expansion, collinear limits, or soft limits, or Regge limits, some limit in which you know the behavior of your amplitude or your integral. Which might be hard to get, but still simpler than the full calculation. Okay, so it's down to what is the ansatz. The R case we know how to get, so it's the T case. But let's first look at the R case. So I can go and compute my leading singularities for the easy integral. And what I get is the following. I get that this integral looks like this. There's a function e of, let's call it for now u and v. 1 minus u z minus z bar plus u is e. By symmetry you conclude it must be the same object. You get the following structure. You compute your leading singularities, you find 2 of them, 2 independent ones. And each of them must be multiplied then by a transcendental function. In this case, you conclude they are the same because the function must be invariant under, well, it must be totally symmetric function in all the points by both symmetry. So in particular, I can swap u to 1 over u, and I get the same function. Okay, is that clear? It's both symmetric, so it must be the same when I exchange, for example, u and v, when I invert u, when I invert v, and so on. The usual symmetry on cross ratios. Now the question is, what is E? So this I have it. Now this is the structure. My E should be made out only of polylogs, if my assumption is correct. So E should be some combination of MPLs of some type. But the question is, which ones? Now, this is equivalent to asking, what is the alphabet? Because remember we said that if I give you the alphabet, then I can construct a space of polylogs out of it by building all possible tensors and looking at the integrable ones in there. So, the question, which polylogs do I choose, leads me to what is the question, what is the alphabet? So what are the entries in the symbol? It's the same question, essentially. Because if you give me an alphabet, I can construct a set of MPLs. Now, what I can do is I can at least go and look at the integrals I know. That should give me some idea. Might not be the full answer, but I should get some idea. In particular, because I see that I get the same z and z bar in the leading singularity, like here. So maybe I can make an assumption that for now the alphabet for the easy integral is the same as the alphabet for the ladder. And what is the alphabet for the ladder? You look at the symbol of, so I have to check what appears in the symbol. And when I look at the symbol of a classical polylog, because that's all I have in here. I have log z bar. So this means that I must have already z and z bar. So this is what appears in the log. In the classical polylog, this is always, the symbol is always this one. This you can check in from yesterday's lecture. So you get z, the argument, but also 1 minus the argument. This is the branch point. The dn has a branch point at z equals 1. So, since this thing is only logs, and classical polylogs, the alphabet of the ladder diagram is this to all the water. So I can make this assumption. And then see if that gives me something that is sensible. But I can construct an ansatz for E that would match some kind of expansion around some limit where I know how to compute. I'm not going to compute the limit because that's a technique on its own. I'm just assuming someone gives me the expansion of these integrals when 2 points become close. So, what I would do then is I would start to write down functions whose symbol has only entries of this type. Okay? And I have to find the integrable ones. But I can actually even do more, because I know this thing is a Feynman integral, so it must have the right cuts. So I know that whatever happens, my ansatz now tells me that the cuts are such that I must have the structure. Okay? Because the branch points must be at Mandelstam invariants, which are these xij squares, and my conformal invariants is it can only be u and v. Which means if I sub in this, the symbol must have the following structure. The first entry is either z times z bar or log 1 minus z, 1 minus z bar. And remind you, this means log of z bar, log of 1 minus z, 1 minus z bar. This is good. This already tells you that my guess that something like z and 1 minus z should appear in the symbol sounds reasonable, because there's c, z, and 1 minus z in there. But this tells me something much more. Namely, well, let's write it in terms of logs, okay? It's cleaner. So it's the same, I just put log. Now, z and z bar are complex conjugate, at least in Euclidean space they are. Now what do I conclude then? That means that this is actually this. Okay? So, that means that under my assumption that I made, well, rather, actually no, not my assumption, the first entry condition, the fact that I must have the right cuts, means that the first entry can just depend on these objects, which have no cuts in the complex z-plane. So log mod z square, log mod z minus 1 square, have no cuts in the complex z-plane. So basically what happens is this statement that these integrals and that the correlator has the cuts predicted by unitarity means that in this variable z there is no cut at all. There's an equivalent statement. Don't get fooled. I don't say that the integral has no cut in terms of u. There is a cut in terms of u, but the statement that there are only cuts corresponding to physical unitarity means that there's no cut in z. That's a one-to-one statement. Okay. So the conclusion at this point, which relies on my assumptions that I have polylogs, so that all this makes sense, that I can look at symbols. The conclusion is that cuts in u and v only, so discontinuity is at this point only, so that is unitarity. Implies that the function is single valued in the complex z-plane, or as seen as a function of the complex variable z. You can, and we will see that. Well, there will be. But you know that discontinuities only act on the first entry in the symbol. Okay, this is a statement about the full thing, but of course if I take iterated cuts, I have no control. This is a statement about the first cut. Okay? Now, this is actually something, when you think about it, that is very general. This should also apply to the ladder integrals. And you can check that the ladder integrals have precisely this structure. And when you show this formula to mathematicians, they will tell you, oh yeah, that's a class of functions that we know very well. Those are single-valued polylogs. Maybe you have heard sometimes mathematicians talk about the Bloch-Wigner-Dye logarithm. This one-loop box integral is what mathematicians would call the Bloch-Wigner-Dye logarithm, up to some conventional things. Okay, so this is a very generic statement. Okay, so Well, this means that I can sharpen my ansatz. I can now say what I'm actually looking for. I'm looking for, so for E, okay? For E up there. I'm looking for a function E, which is MPLs, which has an alphabet which is Z, Z bar, 1 minus Z, 1 minus Z bar, which is single valued, abbreviated as SV. And I can even do a bit more. There are some symmetries. Let's put it in brackets. Which come from the Bose symmetry, for example. For example, if the function is supposed to be invariant here under Z to Z bar, for example, the function must be actually anti-symmetric under this transformation. Why? Because you see, when I exchange Z and Z bar, I get a minus sign, so I better get another minus sign upstairs. And there are some other symmetries which you can work out, which come from Bose symmetry. But that's not the important point. This is easy. The non-trivial statement would be here. In particular this. It's single valued. Okay, so now you can say, okay, but how the hell can I construct this space? What I would now like to do is I would like to solve this. I would like to construct a vector space of functions which corresponds to this. In other words, I would like to have a basis for the vector space of functions that is defined by these conditions. Let's forget about the symmetries, because that is more like for the right linear combinations in that space with correct symmetries. What I want is, I want to have polylogs with this alphabet that is single valued, and I want to have a basis for that space. It's a well-defined linear algebra problem, but I guess you can feel that this is, in principle, not so obvious how to do. Are there questions up to here? Yeah. No, you might fail. Yes. This is an ansatz, okay? It's an ansatz that I can make based on everything I know so far about, so all the 4-point correlator integrals that I've computed in my life satisfies this. So if I had to make a guess for what is the next complicated integral, it would be look in the same space and check if it satisfies when I try to match it to some limit. It might fail. No, wait. Here I'm constructing a basis, then I write down an ansatz, which I match, say, to my OPE prediction, and then of course I need to have enough boundary data in order to fix all the constraints. Okay? I need to get enough data from somewhere. For example, if you think in terms of OPE, I need enough terms in my expansion, which can be tough to get, but still easier than computing the integral. Okay? So what I want then is a basis for, and something else I know is the weight, of course, okay? The weight should be 6, because it's a 3-loop object, 2 times L. For this vector space of functions. So how can I get that? Well, you're looking for a basis. So basis is often the statement about, okay, what are relations among these objects? For example, imagine I could describe the full space. There would still be the question, when are things related among themselves? Okay? then we go back to what we discussed yesterday, functional equations. Such a relation among these elements in that space would be a functional equation among the functions. What I'm looking for is a minimal set. That's comment number one. Comment number two, everything we did yesterday was in the end linear algebra. It was a Hopf algebra, and the underlying structure is a vector space. So it's all linear algebra. And the whole idea behind this Hopf algebra thing yesterday was that it's recursive. I can build up all these relations recursively in the weight. So what I can try to do is I can try to construct the basis step by step. I say, okay, what could possibly a basis for this space at weight 1? Well, that is easy, because at weight 1, the only objects that I have, if I take my alphabet, would be log z bar, log 1 minus z, log 1 minus z bar. Okay. That is the meaning of alphabet, that those are the 4 basic logarithms that appear in my construction. And now you can ask, if I take a linear combination of those, what would be the linear combination that is single valued? Is single valued, and you can easily check it's a linear combination of the type log z bar and log 1 minus z bar. Those are the ones that will be single valued. Okay. Because if I do the monodromy around 0, for example, these two would not have a monodromy around 0, so only these two. And they have opposite monodromy, so it must be such that they cancel. And the same for the monodromy around 1 and infinity. Okay, is it clear to everyone that this is single valued? If not, then please shout. Okay. So, what can I do now? What would be the basis at weight 2? How could I get that? Weight 1 was trivial, that was my starting point. Now I want the basis for weight 2 of single valued functions. How would you go about that? You know by construction that, so let me write, the space that I'm looking for would be weight 2 part of single valued function. Let's take an element in there, and let's act with delta 1, 1. Let's decompose it into 2 objects of weight 1. In general, I would, so this thing sits somewhere, which is called h2, which would be all the functions, and then hsv are the functions in there that are single valued. Okay, like h2, h1 would be the linear span of all those, h1 single valued would be the linear span of those. So when I decompose this into simpler objects, well, the simpler objects will of course be in this space. They would be, at every entry in the tensor I would have these objects, obviously. But since I know that single valuedness means that the first entry must be single valued, that's where all the discontinuities are, it means that I must have this. If I start from a single valued function, I act with the coproduct, then the first factor must itself be single valued. This is nothing but restating what we had for Feynman integrals, that the first factor must have the same cuts. Here it's the same. Here there are no cuts in the complex z-plane, which means that the first entry can have no cuts in the complex z-plane. The second factor is free in principle. Okay? And this thing actually sits in h1, tensor h1. So there's a subspace in here. So this gives me a description of my weight 2 space. I take it, I decompose it, and I get this. So what does it mean? It means that I can now try to go the other way. I can now go and say, I start from here, I write an ansatz for this, and I try to see where it came from on this side. So if I start from this space, then in this space, the most general object I can write down looks like this. C1 log mod z square tensor log z plus C2 log mod z square tensor log z bar plus C3. I'll just list all possible things that I know, because I know the basis here and I know the basis here. And I have the same 4 terms, but with 1 minus z in the first entry. So I have 8 terms in total. Z square tensor log 1 minus z plus C8 This is the basis of this space. And maybe you want 5-minute break and then we're going to solve it as you like. You want a 5-minute break? Yeah. Okay. Okay, so let's try to find the basis for weight 2, basis of single-valued functions for weight 2. So how do you do that? The first thing you need to do is, this is the most general element in this space. But not every element in here has a pre-image in here. Because these things, if you want, are functions. These things are tensors. And we said that not every tensor is the symbol of some function. But it needs to satisfy integrability. Integrability means, well, I need to replace, remember the example at the beginning with x tensor y plus y tensor x. I replace all objects of the type a, b by d log a wedge d log b, and I must equate this to 0. So I do this in here, I replace all the, well, log a, log b here. By this, I equate it to 0. I solve it. And this gives me constraints among my coefficients, C1 to C8. If you do that, it's a very simple exercise. You see that the integrable tensors are these. And there's a fourth one, which is, oops, sorry? There's one missing, namely this. Sorry, I didn't write it down, so I take it from memory. So there might be minus signs somewhere, but it looks like this. Something of this type. Therefore, of course, when I mean this, it means it's the linear span of this as a solution to this thing, okay? Now, the question is now, where did they come from? So each of these comes from an element in here. The first one, I think it's obvious, that comes from log, well, 1/2 log square mod z square. The second one, in the same way, comes from 1/2 log square 1 minus z square. The third one comes from log mod z square log 1 minus z square. So the first three are not a surprise. Obviously, whenever I have a basis at some weight, I can multiply together and I get a basis at the next weight, or at higher weights. Okay, so these are just the products of these two guys. I must have them somewhere. And then there's a new object. So this is a genuinely new object. And one way to see that this object is genuinely new, well, there are various ways of seeing it. One way of seeing is that this tensor is not symmetric, while the others are. So it cannot be a product of logarithms, because products of logarithms give rise to symmetric tensors. The other way to see it is that when you exchange z and z bar, all of these remain the same, because at weight 1, when I exchange z and z bar, I get the same thing. While here, when I exchange z and z bar, since this is a ratio, I change sign. So this is really a new object, and that is this Bloch-Wigner-Dahl logarithm that I mentioned before. You can now go and check what function in here would have such a symbol. The way you would do it is, well, you know which functions live in the full space, write down a linear combination here and check which linear combination has precisely that. That is a function that mathematicians like to call d2 of z, which is defined in the following way. It's the imaginary part. The imaginary part just means anti-symmetrized in z and z bar. Okay. So this is the basis for H2 single valued. I need to get to 6, so I need to repeat this procedure now. So now I can start. Next thing I would want to have is single valued weight 3, which when I decompose it gives me H single valued weight 2 tensor H1. I know the basis of this space now. I know the basis of H1, which is this. I write down the most general linear combination. I check that the tensor is integrable, and I repeat the same thing for higher weights. One caveat, you should add one thing to this basis, which is weight 2, which is zeta 2. We always have to add the corresponding zeta values as well. Okay? So you can, this will give you a basis for, if you repeat this thing for weight 3, gives you a basis for H single value 3, and you go on like that. You can bootstrap your way up and construct a basis for H single valued at weight n. If you do that, that's just combinatorics. It becomes very tedious at some point because you get more and more coefficients and it gets tedious, but it's combinatorial. But you can do it up to weight 6. Actually, you can even do it to higher weights for this case. Then you can write down an ansatz for E in terms of the basis of H single valued 6. You can also make sure that you take the combination here, there's the right symmetry and exchanging Z and Z bar and so on. But more importantly, you can match to boundary data, so some kind of what are called OPE or collinear limits. And what you actually get is, you see that that works. That is the answer. I'm not going to write it down because it's long and it would not tell you much if I write it down, but you can find the answer and you can check it numerically, you get the right answer. Without having done any integral. You just constructed bases of some vector spaces of functions. And you used analytic properties of the Feynman integrals translated into this mathematical language. Okay? So that was one integral. There was another one, the one that was called hard. You can repeat the same game for that integral. Yeah? Yes. Good point. In this case, indeed, actually, maybe I should say it at this point, HSV, the one that corresponds to this alphabet, was actually constructed by mathematicians. So you could go to the literature, they tell you what it is. The reason why I did it brute force here is because in more general cases, mathematicians will not have solved the problem for you, so you have to do it yourself. But indeed, in this particular case, the solution is actually known. Okay. Like this thing is known, and then there's also the D3 and the D4, and even... Well, but you also need other stuff. It's not just DN, okay? You also need like stuff that would correspond to multiple polylogs, but single valued. But this particular case has been solved by Francis Brown in some paper a few years ago. Okay? But I still want to give you the general thing that you always works. This always works, whatever the situation. You can always construct a basis this way. It's tedious, but it works. So, you can now try to do the same for hard. For the hard integral. Okay. You start with the leading singularities, and this tells you that the hard integral should have the following form. You compute leading singularities, gives you the RKs. And let me immediately say that this thing is a function of Z and Z bar now. Z bar squared. There's a function which you call HB. So now you have two different TKs. They are no longer related by symmetries. And an easy way to see that they cannot be related by any symmetries is that here the leading singularity is even when you exchange Z and Z bar. So this function must be even, and here the leading singularity is odd when you exchange Z and Z bar. So this function must be an odd function on the exchange of Z and Z bar, so they cannot be related. Okay. So this is the general ansatz, and this should be your TK, so these should be your polylogs, if such a solution exists. And you can try to play the same game, and you will fail. There's no solution of this type. So the ansatz just doesn't work. For easy it worked, for hard it didn't. Which means that somewhere in your assumptions something was incorrect. And the assumptions that we had is that it is polylogs. Here you wouldn't expect it not to be polylogs, just because, but there's no deeper reason. It was single valued, well that is pretty solid, that is unitarity. And we made an assumption about the alphabet, that the alphabet was the same as for the letter. So you can ask yourself, what would be an alphabet that is more general than what we had so far, that could work. And when you think about it, there was one new singularity that appeared all the time, which was z minus z bar. So what you can do is, you can say, well, let's try the same game for hard, but we not only use these letters, but I also use this one. It's a new assumption. And you do exactly the same thing. You now construct a basis for single valued functions in this space. Well, it's the space built out of these letters. And you try to fit to your boundary data. And you succeed. And you check again numerically. It's exactly the same procedure, except that everything becomes longer now. Because now, before we had 8 terms in our original ansatz, now we would have 10, because you have this one, you have one more. And then if you go to higher weights, it's not just 2 more, but it multiplies, okay? So combinatorics get pretty ugly. At least up to 8, 6, you can solve the combinatorial problem, match it to boundary data, and you're done. So this gives you the full result for all the integrals for the 3-loop correlator in n equals 4, and so for the full correlator. One thing that you pick up along the way, you learn something which is not very deep, but based on what we had here, what would happen if I did the same for the 1-loop integral? It was this one, or written in dual coordinates. This way. This is more like a comment. What would I have learned from this thing? We actually computed its leading singularity yesterday morning. That was precisely this thing, and we got 1 over the square root of the Gram determinant, which is precisely z minus z bar. Okay, so yesterday we computed this thing, and it was 1 over the square root of a Gram determinant. So this would be the t, which is z minus z bar. So one leading singularity, which is z minus z bar. You also know that this thing should be, well, if you believe in polylogs, this should be weight 2. The leading singularity is also under exchanging z and z bar. So this function better be as well, because the whole thing is invariant. But if this is a function of weight 2, it must be a linear combination of these 4 objects. And how many objects you have in here that are also under exchanging z and z bar? That's precisely 1, which is this guy. So, just on pure thought, by pure thought, I can conclude that up to a constant, this integral is actually this. This is just by using symmetries and, well, the underlying mathematical structure of this thing. You can do the same for the double box. You have a few more functions, a handful, so it's not unique. But at least at 1 loop you could just get the answer by the computation we've done, without having to know anything about this integral. Just by knowing its leading singularity and the space of functions, you nail the function completely. Under the assumption that this is the right space of functions, okay? But here I wouldn't even need to match it to any boundary data, it's just symmetries. Okay? Yes? Yeah. If you start with, if you had used this one for easy, then it would still work. That's fine. I mean, what would happen is, in the worst case scenario, what would happen is that, well, you would get a solution. The solution may look different, but it would be the same solution. The only thing that might happen is that, because what this means is if you take, in here you have the alphabet of the ladder. Okay? So when I construct my space of functions based on this, I might choose a basis such that the basis of this space was not manifest. The basis of a function in here, like the D2, might have been written as a combination of functions that involve this ladder where it would cancel, but you would find an answer. The answer might look a bit too complicated, but the answer would exist and would be unique. If you choose an alphabet that is too large, that's no problem, except that then constructing the basis is much, much more complicated, because the combinatorics might explode. But since this, if the alphabet is a subset of the bigger alphabet, then the function space of a ladder will be a subvector space of the other one, so you will find the answer. It's really like Russian dolls, okay? They sit one into the other. Okay? More questions? Yeah, the bound, if you plug in here the same ansatz as for easy, and you try to match it to the boundary data, you get a contradiction. I would need to check how many we had for this one. It also depends on how many symmetries you throw in. So we first, of course, that's something I didn't do with. You throw in all the symmetries exchanging Z and Z bar and all that stuff. This already reduces the size of the ansatz. I think we needed like 10 terms in expansion around when 2 points got close or something like that. But I would need to check the exact number. It was not hundreds. It was also not 2. So, because of course the number that you need is something that is the order of the size of the bases in your space. No. No. The solution is unique because it's a basis. There's the function you're looking for is a point in this space, which has a unique decomposition in the basis. Yeah. You can find a solution. A unique solution, yes. Yeah. But it's unique. Well, no, what would happen is, let's look at the toy example, okay? Say if I use the smaller alphabet, the solution is a plus b, okay? Where a and b are two basis functions that are constructed this way. Now, you had done it with the larger alphabet. You would have found something that looks like c plus d plus e. No, because A might be something. A is itself a linear combination of. You might have used a different basis for the space. If you construct it such that the basis of the larger space has explicit the basis of the subspace, then yes. But if not, then my A and B are linear combination of your C, D, and E. Okay? So your answer might look different, but it would be unique because also CDE would be a basis for the larger space, but such that A and B, which are bases of the subspace, are linear combination of the bases of the larger space. Or if you want a more geometric picture, you have the subspace might be more kind of oblique to the basis you constructed. Okay? But the solution is always unique. It would not be unique if the functions that you constructed are not the basis, obviously. Because then what you would see is there are 3 parameters left over, which are precisely all the functional equations among these functions that you have, because they are related by functional equations. For example, if at weight 2 I have this one, which would be the equivalent of my d2, and I had all possible log z, log 1 minus z, and so on, and also log square z, log square 1 minus z, I could also have thought this one is in there. If I then fit, then there's a free parameter left over, namely which tells me that the following identity must hold. There's a relation of this type, so I would not be able to fix the coefficients uniquely because I have these relations among the functions. But if I construct a basis, it's unique. More questions? No? Okay. So, then, well, this pretty much closes what I wanted to say about the correlator, but then we can go back to our 6-point amplitude and see what we can do there. So I have 15 minutes. Yeah, I can give the introduction and then we do the details tomorrow. So, this is something that people now call the hexagon bootstrap. And what it is about is, it's okay. Remember we had this function here, which I can even remind you what it is. It looks like this. So it's a function of these three cross ratios, u1, u2, u3. Is an L4 xi plus xi minus minus 1/2 d4 1 minus 1 over ui. And then there was minus 1 over 8 squared plus 1 over 24 j to the 4th plus pi square over 12 j square plus pi to the 4 over 72. And I let you check in your notes what j is and what L4 is. This is actually something that looks pretty much like this Bloch-Wigner dialog that we had. Okay, it was some sum of logarithms to the power k and then some leads. And the j's are logarithms. And the x plus and x minus were the ui is x plus minus, which looked in terms of cross ratios like this. There's delta, which I'll let you check in your notes. Well, xi plus minus is ui, x plus minus, and x plus minus is this. And we said that also this in twistor space becomes the cross ratio of things. Okay. The first thing that you can note, which we now understand, we had mentioned as a curiosity a few days ago, but now you should understand why, that there's always weight 4 here. Okay. Now we understand why, because the bound in n equals 4 super Young-Mills is expected to be saturated, so this is what you get. And so the idea is now that we try to do exactly the same now here. What we say is, okay, I know R62, so I can look at the alphabet. I can look at the symbol of this whole thing, and I extract the logarithmic building blocks if you want. And then from this try to guess an ansatz for R63, match it to some kind of boundary data that I will describe. I cannot give you all the derivations because that would be another 10 hours or so. And then you go on like this, okay? Then you know from this, if you make the same assumption, as long as you make the same assumption about the alphabet, and you have enough boundary data, you can try to construct these functions. I'm going to discuss it in the context of this R, which is the MHV case. For the hexagon, there's also a next to MHV holistic configuration. The same thing can be done there, and has been done. But I think just for the sake of the example, it's enough to discuss MHV. The idea is the same. Okay? So I need two ingredients. I need the alphabet, I need the boundary conditions. And of course, I first need to make a big assumption, which is that A, it's polylogs to all loop orders, which for MHV is believed to be the case, and B, the alphabet does not increase when I increase the loop order, which we have seen here can happen. But again, what I do is I make the answers and I check in the end that it's consistent. Moreover, here we have some good ideas to believe that we know the full alphabet. We might come back to this tomorrow if you have time. But for now, it's just making the assumption that the alphabet is the same at all loop orders as it is at two loops. And I see how far I can get. So what is the alphabet at two loops? So R62 is, well, obviously U1, U2, U3, because remember that we said that the symbol of all R6 to the Lth power must be log U1 tensor something plus log U2 tensor something plus log U3 tensor something. So the cross ratios must be in there. You will probably not be shocked when I tell you that also 1 minus the cross ratios must be in there. You see it from here. Okay, so you have 1 minus the cross ratios. And in addition, there is something that you can call U1 to YU3, which are defined in the following way. YUI is UI minus x plus divided by UI plus x plus. Minus x minus. Okay, so I trade x plus and x minus for these y's. Okay, this is just by computing the symbol this thing, massaging it a bit, and you see that that's what comes out. And so the next thing you can do is you can ask yourself, okay, what are the boundary conditions? There's of course there will be three classes. The first one is very generic. So there's, for example, the first entry condition, which is this, okay. the first entry must have this type. There's also something which was specific to this case. I don't have time to discuss. The second entry is also highly constrained. The second entry is either ui or 1 minus ui. It comes out, I think, of the memory as well. When you look at the supersymmetrization of the Wilson loop, you see that this must happen. Another way of seeing it is when you think of, remember that I told you that the coproduct of a Feynman integral must have Feynman integrals themselves in the first entry. The Feynman integral at 6 points at weight 2 that is conformal would be the 2 mass easy box, which is basically the dialog of 1 minus the cross ratio. The y's do not appear at one loop at weight 2. And the third one is also a last entry condition. That one does come from some analysis of some supersymmetrized Wilson loop, where people concluded the last entry is either a y or not a y, but then it can only be this ratio. The fourth one, which is total symmetry. That is just both symmetry. Or rather, since I'm color ordered level, it's the dihedral symmetry of the 6-point amplitude. Remember that I have one cyclic color ordering, and I can rotate cyclically because my trace is cyclic. That translates in terms of the U's into total symmetry. When I do a cyclic rotation of the external momenta, I permute U's. And there's a fifth one, which is parity. It's the equivalent of the symmetry between Z and Z bar that we had in the correlator. You see that here I can exchange x plus and x minus, which is like complex conjugation. Change the sign of the square root, which means that I invert all my y's. But the object that I'm looking for is real, so the function must be even. The function I'm looking for is even under this transformation. The same as for Z and Z bar in the correlator. Okay. Those are some very generic constraints that I have. I guess you will not be surprised if I tell you that this is not enough to fix the function. Okay, these are very generic statements. This is a statement about the first entry, the second entry, the last entry, and some symmetry consideration. So I need some kinematic data as well. So I need the equivalent of, say, my correlator when 2 points become close. And their statement is, it's called a 6. I can first of all look at collinear limits. Okay, so this thing is what was left over after I removed the piece that exponentiated over the 6-point amplitude in a specific color ordering. Okay, so I have P1, P2, P3, P4, P5, P6, and I remove the piece that I got from exponentiation. Equivalently, this thing is a hexagon. P1, P2, P3, P4, P5, and P6. Now, imagine I make 5 and 6 collinear. Okay, they go collinear. Or equivalently, in my Wilson loop, this means that basically the picture would look like this. Okay. This means that when 5 and 6 become collinear, or any other two neighboring momenta for that matter, then my hexagon becomes a pentagon. But we said the first time that there isn't a remainder function is at 6 points. 4 and 5 points I get exactly from exponentiation. This means that R6 at any loop order must go to 0, because there was no R5. R5 is 0. Okay? Now you can look at what this constraint is in terms of cross ratios. It is not an easy one. It means that one of the u's goes to 0, but the other two do not go to 0. So it's actually a statement that when one of them goes to 0 and the other ones, I think, sum up to something finite, then the function must vanish. You can work it out. You just need to check what it is, but you can easily convince yourself that when 5, 6 goes to 0, one of them will vanish. Now, just like for the correlator, this is like the first term. For the correlator, say we have an expansion around the limit, like an OPE expansion when 2 points become close. And we needed also subleading terms. The same is true here. So this alone is not enough. We also need the subleading terms. In the collinear limit. And this comes again from some OPE, which goes back to Bassos-Heven-Vere. But to describe this will take more time. So I guess then now is a good time to stop, and we continue tomorrow, because this will take more to explain what happens. Just in simple words, what will happen is we will get an expansion around the limit where these two edges are collinear. And I can use this as boundary data. Just like for the correlator. Okay? But we do that tomorrow. Good. Questions? Okay, then enjoy lunch.